Now here I'm going to discuss about ultimate limit state beam design and the rectangular beam section. So if we have a beam, a 3D beam such as this, and we need to determine the strength of this beam, how much moment can it support, and here we're going to look at the stresses in the beam. If you section a beam at the center and the section XX, this is the face of the section. So at this face we're going to look at the stress changes from the top to the bottom to up to the passing through the neutral axis. So this section XX can be also drawn as here. If we have a reinforcement AS, area AS, and we can see that the neutral axis is somewhere here, which is denoted by NA. So above the neutral axis we have maximum strain. When you look at the strain diagram, maximum strain is the code specifies is 0.003, that is BS8110, and the maximum strain at the bottom is 0.002. That is in tension. So the stress diagram now looks like this. We have a parabolic stress that is actually nearly exactly what happens in the beam. The stress distribution is parabolic in nature. So we have this curve, which is a parabola, and a compression on top on the concrete, and a steel provide the resistance, which is TS, the force in the steel. So the code modified this stress block for simplicity of analysis and design. So now we have a rectangular stress block with intensity equals to 0.67 FCU, and we have the centroid of this force acting, resultant force from the compressive force is here, acting with the resultant of CC. Now the distance from top to the neutral axis is denoted by X, and the distance, the stress block, depth of the stress block is beta X, and beta is a factor that accounts for this change in shape. Say we had a parabola, and now we're using a rectangular stress block. So the distance between the two forces in concrete and steel, CC and TS, is the lever arm, which is denoted by Z. This Z. Now when we come to the analysis here, we will go to equilibrium of forces. So we have this force CC, which is a compression in concrete, and the TS, which is a tension in steel. Now when we get the summation of forces in the horizontal direction, that is summation of forces in this direction, should equal to 0. So if we do that, then we will end up with the TS should equal to CC. Now this means the tensile force at the bottom should equal to the compressive force on the top for equilibrium to occur. So the maximum moment therefore can be equals to the force in concrete times the lever arm, which should also be equal to the force in the steel times the lever arm. Now the code BS8110 specifies that beta should equals to 0.9. So if beta is 0.9, then we have the force in steel, TS, is therefore equals to the yield strength of steel times the area of steel out of material factor of safety, that is the steel, and therefore the force in concrete is also equals to 0.67 times FCU, that is the strength of concrete, out of material factor of safety, which is this for concrete, times 0.9. Now this is beta x, beta x, so it is beta x, that is 0.9x times b, that is the width of the beam. So this portion here, 0.9 x times b, is the area of this stress block. So this is the area, and this is the this portion here is the stress. So this is the stress in the block, in the beam section. So if we see, it is force is equals to stress times area, that is it. So equally here for steel, you can see it is this Fy over material factor of safety is also stress times, so this is the stress times area, the area of steel, so it gives you force. So what we are doing here, we are multiplying force, stress times area, it gives us the force. So this is how we come up with this. And now we can see that Z, if we need to get the ultimate moment, we need to get the value of Z, and Z here is equals to D minus 0.9x out of 2. So we can go further with this, and for under reinforced concrete, beam, the code specifies that the neutral axis x value should be less than or equals to 0.5 D. Now let's get in and substitute the values. Also, the material factor of safety for concrete is 1.5, and the material factor of safety for steel is 1.15. But for now, we are going to get the maximum moment using the equation for the concrete section above, because we can specify the size, the geometry of the section, and then we determine how much reinforcement goes into it. So it is easier to go with the concrete section. So here we can say our value now will be 0.67. we substitute the values here, FCU out of, instead of, this is now the material factor of safety, times 0.9 times, instead of x we say 0.5 D times B into Z. Now Z is D minus 0.9, where there's x we replace it by 0.5, because that is the 0.5 D, that is the maximum value of x specified by the code out of 2. The minimum value of x specified by the code. So M ultimate is therefore equals to, if we multiply this out, we get 0.201 B D FCU into D minus 0.225 if we multiply this and divide D. Now if we subtract this, this will be MU is equals to 0.201 BD FCU into 0.775 D. if you subtract the d minus 0.225d, and mu therefore is equals to 0.156 FCU BD squared. So this is the ultimate moment a rectangular beam can support according to the British standard 8110. Thank you for watching.